Well, we are at the hour, and we do have a lot to cover today. So let's go ahead and jump in. Good afternoon, everyone. Welcome back to our monthly ML plus X forum. My name is Chris Endemann, and I work as a research cloud consultant for DeWitt's Research Cyber Infrastructure office here on campus. And I also help lead the ML plus X community here at UW-Madison. Today, I'm really excited to be joined by Nidhal Jegham, who's a incoming CS and stats graduate student at the University of Rhode Island. He's also the lead author of the paper How Hungry is AI, which is a benchmark study that measures the energy, water, and carbon footprint of large language model inference. Before I hand things off to Nidhal for the majority of the next hour, I just want to share a few announcements and also discuss why we have selected this topic for today's forum. Here's my example, Exhibit A. So this is a graph showing the wildfire smoke across the US and Canada. And this summer, I had to buy two air purifiers just to get through the Canadian wildfire smoke. And this was a good reminder that climate impacts are kind of no longer abstract. They're right here in our daily lives. And this is just kind of a microcosm of more serious issues for many states and countries and ecosystems. A rapidly changing climate has been taking its toll for many years, if not decades. Now, AI didn't start the fire in Canada, but I guess the question is, will it add to it or help put it out? It being a metaphor for increasing number of climate disasters. So I'm generally a really strong advocate for machine learning and AI. I've led this forum for the past 4 years where we talk about ML and AI every month. But I will say that these systems come with real costs and that we need to balance these costs and take them into consideration as we're working with machine learning and AI. So I don't think the goal of this event is to convince you to stop using AI at all, but I think it is important to think about how to use it appropriately and try to make informed, sustainable choices while still delivering strong outcomes. So over the summer, well, after I guess breathing in too much wildfire smoke, I started thinking about whether or not there was a way we could try to build a sustainability focused project into our annual machine learning marathon event. And for those of you who aren't aware, this event is basically a 3-month hackathon where we host a bunch of different machine learning and AI applied projects. And then teams team up together to try to tackle those projects together with advisor support. And so one project that I thought of was to basically tackle this issue here, which is that many practitioners don't really have a clear sense of their workflow's environmental footprint in terms of AI and machine learning. And so how can we try to make that information easier to retrieve and easier to act on? And so in this challenge, this Kaggle challenge, teams will build AI systems that extract environmental impact estimates from over 35 papers and industry reports. And the system must output citation-backed answers or explicitly indicate when evidence is missing from the provided corpus or set of papers. So how are we going to do this in this challenge? The basic technology is going to be retrieval augmented generation, or RAG. And if you haven't heard of RAG before, my kind of 1 sentence or 1 minute overview of this technology is that given a question, we're going to use a large language model to then scan a corpus or a set of documents for relevant evidence that answers our question. And that could be things like quotes, data from figures, or data from tables. And then after we've retrieved relevant evidence for our question, we're going to input that evidence into another large language model and then ask that model to answer our question using the provided evidence as context. And the idea is that by using this sort of setup, we can help prevent large language models from hallucinating or providing answers that are incorrect or not based in reality. So just to give you a little bit of more details here about this data set and how we've built the challenge, we have, again, over 35 papers, and these all kind of cover different subfields at the intersection of AI and sustainability. And then with the help of my collaborators, DJ Paul and Annie Zhao, we have contributed over 300 question and answer pairs that dig into the key insights of this corpus. And so these pairs are designed to stress test your RAG systems. And a successful RAG pipeline will be able to recover all of the answers from this data set. Now, I think the best way to get a sense of this is to look at some examples. So just to give you an idea of the questions and answers that we have crafted, some questions are going to be kind of simple quote lookups. So here we have a true or false question. And to find the answer, we have to look at Lee 25, this reference here, and we need to find this quote here. And this quote, it will then answer this true or false statement. Some questions require evidence from multiple documents in the corpus. So here we have to combine information from both an Amazon report and from Lee 2025. Some questions require reasoning or simple math. So here we're trying to extract the average US household electricity consumption, as well as the amount of energy it takes to train a 6.1 billion parameter language model. And after you retrieve those two pieces of information, we can run this simple calculation to then derive the answer here. Some questions in this challenge will require you to accurately parse data from tables. So here we have to extract this value of 1438 from this table. Some will require you to do some visual reasoning. So in this example, it requires your RAG system to look at the difference between this green point here and this orange point here, and then determine that that difference is around 40%. And then finally, some of the questions are intentionally out of scope. So we might ask things like, what was the total electricity consumption of Google Cloud TPU pods worldwide in 2023? And that information is simply not present in our 35 plus papers and documents. And so the correct answer to a question like this would be unable to answer with confidence based on the provided documents. So I hope that gives you a sense of kind of the different kinds of questions we built into this challenge. And again, the end result that we're building here is whatever team builds a RAG system that can answer all of our 300 plus questions successfully is effectively going to be building a system that practitioners can then use to ask very practical questions like, how much energy will it cost me to design or to build my RAG pipeline for the WattBot challenge? You can go in the reverse and then start investigating your own energy use by using this RAGBot system. All right. So I think I've eaten up too much time already, and I want to hand things off to Nidhal. So WattBot pulls together dozens of papers and reports on AI's environmental footprint. One paper that we found really, really interesting as we were building this challenge was from Nidhal. And his paper is How Hungry is AI, which is a benchmark study that looks at the energy, water, and carbon cost of large language model inference. So I'm pleased to hand things over to you, Nidhal, and I'm looking forward to you sharing your findings, and also I hope everyone else gets a sense of some of the detail and insights that we have present in our corpus for the WattBot challenge by listening to you. So whenever you're ready, I'll stop sharing my screen.
Sure. 1 second, I will share. Perfect. So firstly, thank you, Chris, for the invitation and leading this project. I'm happy to be with you today. So as I said, my name is Nidhal, and I'm a lead author of the study. Today, I'll be presenting it with a colleague of mine and a very good friend, Chan, is in the meeting with us. So basically, today we wanted to talk about, of course, how we got the data, how we developed the methodology, what conclusions we drew from the results, and so on, and of course the future directions and the limitations of the study. However, we also wanted to make it like a quick overview surrounding the field as a whole, the sustainability and AI field, to give you an idea about the foundational concepts and all you guys need to know in order to understand the papers. And I hope that will help you with your project. So feel free to interrupt me in whatever section I'm talking about during the presentation. Ask all the questions you need to ask. There are no stupid questions here. And of course, we will have a Q&A session later on. Okay, so let's say we live in a perfect world where we have all the data we need to. One second. Where we have all the data we need to use. There are no issues with transparency whatsoever. How can we actually compute or estimate the total life cycle environmental impact of LLMs? Well, it's not only about how much energy the training consumes and how much energy each query consumes. The picture that doesn't really paint the full picture, and it's much bigger than that. If we're gonna do that, first we need to start with the supply chain, which can be upstream or downstream. When we're talking about the upstream supply chain process, we're basically talking from the step of extracting the resources needed to, like, there are minerals like the gold and so on to manufacture the GPUs or the hardware to manufacturing them, to then transporting them to their respective destinations, which is data centers. And of course, when we talk about the downstream, basically talking, for example, about the end users. When we are sending like requests or queries to ChatGPT, we need to estimate or measure also the energy consumption of our own computer or server. So to give you an idea about this process, in order to extract the resources, manufacture and transport a DGX of H100, which is basically a server with 8 GPUs together, and of course with their CPUs and everything, we basically have, it basically emits over 1.3 tons of CO2 equivalent. To put that into perspective, this is basically equivalent to 15 transatlantic flights from the US to London. So that's only to make one server or TGX, where, for example, XAI, or the company of Elon Musk, have over 200,000 GPUs. So that gives you an idea about its total emissions, just for the supply chain. And then, of course, we need to talk about the infrastructure. When we talk about that, we're basically talking about all the steps involved into constructing the data center itself, from building the walls to making the ventilation or cooling system to putting the servers into place. All of that needs to be taken into consideration. And then we have to measure or estimate the design impact. When you're talking about design, first you need to talk about data collection, which is basically servers running nonstop for long durations of time, scraping data and collecting it from all over the internet. Additionally, we also need to talk about data labeling, which sometimes is a manual process, sometimes it's an automatic process, which is also very energy intensive. But even beyond that, even the architectural choices that the researchers do, like, for example, are they going to use a dense network or like a mixture of experts or chain of thought, whatever their choice they would do, that requires experiments. And experiments require servers, and servers are actually very energy intensive. So we need to take that into consideration as well. And then, of course, we go to the major ones, which is basically training and deployment. When we're talking about training, so honestly, some companies are being transparent about that, like the Meta company. However, what they share is basically the only successful training attempt. And we need to take into consideration that a lot of attempts are unsuccessful. And it's very rare that the first one succeeds. So we need to take all the training attempts into consideration, which takes us to our next point, which is deployment. Deployment, we need, of course, to take the server energy consumption into consideration, but also the overhead of the data center, which we will dive deeper later on. But as you can see here, we try to do circular arrows instead of linear ones because it's not a one-time process. They do a lot of training attempts, then they get a successful one, then they release the model to the public. And once the public starts using it, of course, feedback will be sent back to the company. And the company would try to optimize the model or make it up to date. Therefore, they have to run the training over and over again. So it's basically a periodic cycle where they train the model, they release it, and then they go back. And of course, we end up with the end of life step, which is whatever decision they do, maybe they want to recycle the GPUs after using them, they want to combust them or put them on fire, or maybe sell them. Whatever decision they will make, it will have its own environmental impact, and that should be measured. But as I said in the beginning, this is a hypothetical scenario where we have all the data. Most of the time, we have no idea about most of the steps here, which is why we tried to come up with this paper to cover maybe one or two steps of this entire process. So moving on to some key concepts we need to know is firstly the energy consumption. The energy consumption can be categorized into three things. Scope 1, where we talk about on-site fuel use, which is basically the backup generators that are in the data center in case of power shortages. But This rarely happens because they rely on the national grid and so on. So we can say that scope one can be negligible. For scope three, we're basically talking about the supply chain, from extracting the resources, manufacturing them, or the end user's energy consumption. All of that needs to be taken into consideration. However, as you know, we don't have much data due to lack of transparency. So the scope three specifically is very hard to measure. And then, of course, we talk about scope two, either for training or inference. So for example, for inference, let's take an example that, I don't know, GPT-5 consumes 2 watts per request. So the server itself consumes 2 watts, but we also need to take other stuff into consideration, which is the data center overhead. We're talking about the cooling system, the ventilation, the data transmission, and so on. All of that needs to be taken into consideration. Therefore, we have this metric, which is PUE, or power usage effectiveness, which is basically the ratio of the total facility energy used to the IT equipment. So if GPT-5 used 2 watts and we have a PUE of 1.5, the total energy consumption of inference is 3 watts, 2 going to the server and 1 going to the overhead. The next thing is, of course, water consumption and withdrawal. I saw someone mention it in the messages before. So consumption basically refers to the evaporation of water from the ecosystem. However, withdrawal is just basically taking the water, using it, and discharging it back. And this can also be categorized into site, source, and supply chain. Site, we're basically talking about the cooling systems. As you know, servers are very computationally intensive and need to cool down. This is why we rely mostly on water cooling methods. Air cooling can work, but the servers are way too big to rely on air. So we use water. And to estimate this or measure this, we basically use WE site, or water usage effectiveness, which basically refers to the liters of water consumed for each kilowatt of energy delivered to the IT equipment. For source, as you know, the grids to generate electricity require water. Therefore, we use WE source, which is basically how many liters of water were consumed for each kilowatt of electricity purchased. And for supply chain, as you know, manufacturing GPUs or extracting resources or transporting them can consume water. So all of that needs to be taken into consideration. However, I also have to raise the point that the supply chain process is very complex and there's a huge lack of transparency regarding this aspect. So it's very hard to measure. And of course, carbon emissions, which can be also categorized into scope one, scope two, and scope three. For scope one, we're basically talking about the backup generators or any gas emissions happening inside the data center. And for this, we use CIF or carbon intensity factor, which is like the WUE, is basically how many kilograms of CO2 equivalent were emitted for each kilowatt of energy on site. For scope two, we're basically talking about the grid itself, how much carbon it is emitting. We use CIF scope two, and for scope three, we use CIF supply chain. Also, I have to raise the point again that this scope three part is very complex to measure, and we usually don't have a CIF for scope three directly to use. And now the last thing before we dive into the paper is I want to explain these two concepts, the location-based versus the market-based. So let's use this example that there is this data center in Arizona that uses around 5 megawatts of power each month, okay? And it's relying on the coal-driven grid in Arizona. So the location-based approach basically looks at that and says, okay, so its total energy consumption is 5 megawatts. However, the market-based approach basically looks at that. It says, okay, it is using 5 megawatts of energy. However, this company itself has invested in solar panels in Texas that are generating maybe 2 megawatts of energy. Therefore, when measuring the energy consumption, we need to subtract all of that, leading us to get an energy consumption of only 3 megawatts. It is up to you guys to which method you find more sound or logical. Personally, I believe the location-based approach is the more sound one because that's the actual energy consumption. And the market-based approach can underestimate significantly the environmental impact of AI. And it's actually been used by the recent Google paper that we will talk about later on. So starting with the related work, I want to talk about this paper, which is honestly a foundational paper in the field and that actually inspired me to start working on this project. It is by Professor Ren and his colleagues, making AI less thirsty. So what this paper basically tried to do is that it looked at the energy consumption of GPT-3 for training it for inference. And by using the multipliers I told you about, like the WOE, it was able to estimate the energy consumption of inference. And it showed us significant differences when looking at the difference between, for example, data center in Arizona or data center in Texas. Because as you know, for example, we are in Rhode Island. When we send a request to the data center, it basically goes to a different one than the one you guys go to when sending it from Wisconsin. So as you can see here, for example, in Arizona, in order to consume half a liter of water, you only need to send 16 requests. However, in Texas, it's around 65. So this paper firstly shed light on the environmental impact of AI in terms of water consumption. It showed the variations in data centers and how the hardware they're using, the grid they are relying on, can impact heavily the environmental impact of LLMs. However, this paper relied on prior knowledge of the energy consumption of GPT. Therefore, it was not scalable and it cannot be reproduced for other models, especially proprietary ones. Second project I want to tell you about, which is honestly a very innovative project. I found it very interesting, which is the ecologist calculator. What these guys basically do is that they found benchmarks online surrounding the energy consumption of open source models on different tasks, and they trained a linear regression model on them. So by estimating or putting the number of parameters of any model and what type of architecture they rely on, they can estimate its total energy consumption. It's not only energy consumption, but also carbon emissions and water consumption. I think using machine learning is very interesting. However, if the shortcomings or what they didn't account for was firstly the batch size, because as you know, we're not using, whenever you send a request, you're not having a server for yourself, you're sharing it with other people, and that reduces the environmental impact heavily. At the same time, it does not take into account the overhead and the infrastructural differences or the hardware differences. Some models rely on different GPUs or technology in itself, which can change the values significantly. A third project I want to tell you about is the AI energy score, actually conducted by people I look up to in the field, where they basically took a lot of open source models and they ran them through different tasks to estimate or measure how much energy they consume. Later on, they tried to rank them or score them based on how accurate and how efficient they are. So the best models are both the most accurate ones and the one that can do it with the least amount of resources. However, this project also does not take into account the differences in hardware and, of course, environmental multipliers. Finally, we need to talk about the Google paper, which has been uploaded 2 weeks ago, that basically give us an idea about the total environmental impact of Gemini models. However, looking closely at it, it does not give us per model, it actually gives us the median of all of the Gemini fleet models, from the big one with extended thinking to the very small one. So giving us the median doesn't really give us an idea about how much these models are actually consuming. Additionally, they relied on the market-based approach. So by taking the initiatives done by Google to reduce their environmental impact, they managed to reduce the water consumption or carbon emissions of these models significantly. So I do believe that doesn't paint the full picture, but we need to appreciate such initiatives because last year, for example, we didn't have any. And finally, we need to talk about the Mistral report, which is, I think, the most transparent report up to date, where they didn't only give us how much inference and training costs, but they also give us the data center construction, model conception, hardware embodied impact, and even end user equipment. This paper honestly shed light on this problem, but the only thing lacking was they did not give us the multipliers they relied on, and they did not give us the energy consumption, making it very challenging to actually reverse engineer it. And of course comes our paper, where basically what we try to do is that by reading environmental reports, sustainability reports, and the purchases of these companies, we were able to infer what type of hardware they're using. And of course, by using statistical methods, we also noticed some discrepancies. And by scraping the data surrounding their performance metrics like tokens per second generation or latency, we were able to develop a methodology that can estimate the environmental impact in terms of energy, water, and carbon for both proprietary and open source models. So To summarize, we tried to do this table to showcase everything. As you can see here, most papers either rely on a specific number of models or are not infrastructure aware, while our paper basically tries to focus on inference to give us per prompt environmental impact. We tried not to measure scope 3 and scope of water and carbon due to the lack of transparency, but we made sure that we are infrastructure aware and we take both proprietary and open source models into consideration. So starting with the methodology, we'll go through model selection, hardware estimation, how we got the data, what was our methodology or equation, and how we converted it to water and carbon, and ending with the DEA eco-efficiency score. So what you basically try to do is we took the most up-to-date models by May of 2025 when we released the paper, which were GPT 4.1 and Claude 3.7. So by reading these reports of these companies, we were able to infer what type of hardware they're using, which is basically DGX H200 or H100 for most models. However, we noticed, and we'll show you how, that the older models of OpenAI, like GPT-4, GPT-4 Turbo, or 4o Mini, actually relied on older architecture, which is the H100. And the only exception was China, which is due to restrictions in exports. Chinese companies are not allowed to use the latest GPUs. Therefore, specifically for them, NVIDIA made the H800, which is very similar in terms of architecture to the H100. And that's what they use to train and do inference for DeepSeek. Later on, by reading also the reports of these companies, we're able to find the environmental multipliers they rely on, like POE, CIF, and so on. For DeepSeek specifically, we were unable to find that, so we used the values of the most 30 efficient data centers in China. We believe that that reflects better the actual values, because if we use the national average, that would not give us the full picture, because small data centers are usually very inefficient compared to large ones. Later on, we tried to classify these models by the number of parameters. So between 1 and 20, they basically need only one GPU to do their tasks. Between 20 and 40, they need two. Between 40 and 70, they need four. And for models bigger than 70 billion, we basically need 8. But of course, you have the question, for example, that how about GPT-4? It basically has like 1.8 trillion parameters. How is your classification only like above 70? And for that is that large models like GPT-4, GPT-5, or Grok that have trillions of parameters actually use most likely use mixture of experts, which is basically agents or experts inside the model that have like 100 parameters, 150. And whenever you send a request, not all the parameters get activated, but only like 1 or 2 experts. So it's like only 200 billion parameters. Firstly, to make the model efficient. Secondly, because it's very hard to run or to change the parameters or use all of the 1.8 trillion parameters at the same time. You'll need like tens of servers to run that, which is very inefficient. So for the A100 or the GPT-4o Mini, what we notice is that when we look closely at the data, we found that although GPT-4o Mini is much smaller than GPT-4o, its speed or token generation per second was actually much lower, which doesn't really make sense, because if it's smaller, it should be much faster. So we tried to dig deeper into this issue, and we noticed the following, is that GPT-4o Mini, when used by the OpenAI API, is actually slower than GPT-4o Mini used by the Azure API, which poses even more questions that got us even more confused. So what we actually tried to do is that we contacted the community, we posted in the community support, and we noticed that GPT-4o Mini overnight, around 9 months ago, got slowed by 6 times. So let's say it had like 16 tokens generation per second, it went down to only 100 overnight, and that never improved again, which proves or gives us the assumption that most likely they deployed it on older architecture. So our assumption was the following, that OpenAI GPT-4o is deployed on the H200, GPT-4o Mini from Azure is deployed on the H100, and GPT-4o Mini from OpenAI is deployed on the oldest one, which is the A100. However, in academia, you cannot just assume and move on with your life. You need actual proof. So what we basically did is that we tried to run an ANOVA test and 2K HSD to notice the following, So we took that Azure is deployed on H100 and we compared it to OpenAI either used on A100 or H800 to see if these differences are statistically significant or just normal value variations of the same type of GPU. For small queries, we noticed that it's basically the same and is statistically significant due to how short the query is. However, as the query size gets bigger and bigger, we notice that these differences become statistically significant, saying that most likely these models or GPT-4 Mini is most likely deployed on A100. For GPT-4 and GPT-4 Turbo, firstly, they were deployed on A100 and their performance did not increase whatsoever over time, making it more likely that they were not deployed on the newer architecture. Okay, so for the data, we basically relied on the artificial analysis website, which is an independent benchmarking website that tries to measure how fast the models are, how accurate they are, giving us an idea, for example, about how many tokens they generate per second, or how long it takes to generate the first token, which is the latency. And we scraped all the data from all of this for all the models. Later on, we started developing the methodology. So for the methodology, the first thing we needed to understand or measure is how much power these models are actually drawing from the GPU. As you may have seen here, we have put the total critical power of the GPUs. However, these GPUs are not being used at their full capacity almost never because that doesn't make sense. They function at around 60 or 70% of their max power draw. So we came up with this equation. We basically look at how many GPUs are actually active in the system. We multiply it by how much power each GPU is drawing, and of course, dividing it by the total number of GPUs in the system and the batch size. We made sure that the batch size is accurate because, for example, and it was 8 in this case, because, for example, if you increase it to 16, that can almost divide the energy consumption by half. And of course, reducing it to 4 can multiply the energy consumption. So we also included sensitivity analysis in the paper about this stuff. But as we've seen from the performance and everything, the most likely batch size is usually 8. For utilization of non-GPU components, we basically did the same. However, we used the power draw of non-GPU components, which is basically 50% of the total power draw, which takes us to this table, where you can see that we did this is the values we come up with. For the H100, H800 and H200, we basically use the same power draw with the H100 because they are drawing the same amount of power. However, their performance differs and how fast they can generate tokens. So over 1 second, for example, H200 can generate 300, while the H800, A100 can generate 200, and the 800 can generate around 100 tokens. However, the power draw is still the same. The changes are only in terms of performance. For the equation, we basically built this thing. So it can be actually divided into 2 parts. First is the total inference time, where we take how long the query is in terms of tokens and divide it by TPS, which is how many tokens are being generated per second. And we add to it the latency, which is basically how long it takes to get to the first token generation, which can be instantaneous, like 0.3 seconds, or if it has extended thinking, it can reach even 6 minutes or 7 minutes. And of course, we divide it by 3600 in order to turn it to hours from seconds. For the second part, we basically take the total power draw of the system, of the GPU, and multiply it by the utilization rates we got from here. For the non-GPU components, we basically take the same thing and multiply it by utilization rates. However, as I said before, only measuring how much the server is consuming does not paint the full picture. You need to take into account the overhead. Therefore, we multiply all of this by power usage effectiveness. For the water and carbon, we basically take the energy consumption and divide it by PUE, because I don't know if you remember, we said that WUE site takes care of the IT equipment energy use, not the total server and not the total data center job. So we have to divide it to get rid of the overhead and then multiply it to get how much water is being consumed for on-site cooling. For off-site, we basically take the total energy consumption and multiply it by WE source. For carbon, it's a very basic multiplication. We just take the energy and multiply it by CIF. For the DEA eco-efficiency, this is basically a ranking or scoring system that tries to find which model can perform the best while consuming the least amount of resources. So in this case, the resources are the energy consumption and the environmental multipliers. So and the output is of course a weighted average of the most known benchmarks out there. So what this model is basically trying to find is which model can have the best accuracy from the output with the least amount of resources from the input. And the results that we came up with, we actually thought that how do I say this? The static table on the paper does not really paint the full picture because the values change every day. Sometimes it changes even 3 times per day. Therefore, we tried to build this dashboard that incorporates even newer models like GPT-5 or Google models and so on that updates on a daily basis and add new models. So one of the most interesting things we've noticed is, I don't know if you can see this here, but DeepSeek is one of the most energy intensive models there by far, which doesn't really make sense because when DeepSeek was dropped, they said it's one of the most efficient models out there. And it actually got us thinking, why did we find these values? But looking further into this, we noticed that this problem comes from 2 reasons. Firstly, the inefficiency of data centers in China. Compared to the US ones, they are not optimized in terms of water consumption or overhead. The second reason is the restrictions on GPUs. Using the H800 makes it much slower, so it consumes more energy to deliver the same amount, the same task. So as you can see here, for a medium-sized query, it basically consumes over 70 watts. And in terms of water, for example, it consumes almost half a liter of water for a medium-sized query. So we tried to do something, is that we found that Microsoft actually deployed DeepSeek on their data center. So we tried to look at that, and we noticed something very interesting. So if you look at DeepSeek, for example, R1, it consumes 70 watts when deployed on DeepSeek data centers. However, when deployed on Microsoft, it consumes only 18, making it actually one of the most chain of thought reasoning models, one of the most efficient ones. And for DeepSeek V3, it's from 24 watts to only 2 watts, divided by almost 12 times. For Carbon, we also notice the same picture, the same pattern from half a liter of water to only 64 milliliters, and from 172 to only 7. So to give you a perspective, using DeepSeek medium-sized prompts 100 billion times is basically equivalent in terms of water to the annual drinking needs of 41 million people. Or in terms of energy consumption, it is equivalent to the annual energy consumption of 650,000 US households. However, something else we notice is that how varying the results are. So for example, for water, from DeepSeek consuming half a liter of water for medium-sized query, to Llama Maverick only consuming 0.45 milliliters. So what we notice is that there is a direct correlation with, firstly, the model size, how many parameters it has. Secondly, we notice that the architectural designs, for example, if you do chain of thought reasoning, those models will consume much more energy or water, or will have much greater environmental impact. Why is that? That's due to how long they take to do inference or to finish the query, because extended thinking requires extended thinking, so it takes more time to do inference. For our DEA, we noticed that Claude 3.7 actually came at the top. So that means it's one of the best models to balance between accuracy and environmental friendliness. And of course, DeepSeek that are deployed on the DeepSeek data centers actually came in last, not due to accuracy problems, but due to how environmentally unfriendly they are. But an interesting point we noticed is that although Llama models are one of the most efficient models out there, they came in last, not because of not being environmentally friendly, but actually due to low accuracy compared to new models like O3 or O4 or Claude 3.7. So in order to rank high in this DEA, you need to balance between both. We actually also tried to do a GPT-4o case study over surrounding how much energy or water or carbon it would consume in 2025. And the results were very interesting. For example, Over the course of 2025, at minimum, GPT-4o will consume as much energy as 35 US households annual energy consumption. In terms of water, it will consume at minimum as much as the annual drinking needs of 1.2 million people. And in terms of carbon emissions, we basically have to plant a forest of the size of Chicago every year in order to offset these emissions. So what type of conclusions can we draw from all of this? Firstly, the critical role of regulations and policies. As I showed you before, Mistral actually showed us the environmental report or the total life cycle assessment of their model, not because they want to do that, but because the EU AI Act obliges them to do so. So they are required to share what type of data they train their models on, how their models perform, they should be open source, and of course, the environmental impact. Compared to like the US, the US recently passed a bill to stop AI regulations for 10 years, making the AI companies not obliged at all to publish proprietary open source models or give us even a glimpse surrounding their environmental impact, let alone China, where we have no idea even about the environmental multipliers. So we do believe that regulations are very important for this emerging technology, and to put these kind of policies and transparency rules can actually help us move forward. Secondly is the critical role of infrastructure in AI sustainability. As you may have seen, DeepSeek, although it is one of the most efficient models out there, it actually was the most energy intensive one, not because of its architecture, but because of where it's deployed. So the type of GPUs matters a lot, and of course, the efficiency of the data center matters even more. And now I want to tell you about the Jevons paradox. Some AI companies or some AI enthusiasts say that we should not worry about the environmental impact of AI because over time it will become even more efficient. And AI itself will help us make AI more efficient, which is something I agree with to a certain extent. However, the Jevons paradox says that when a technology becomes more efficient, that doesn't correlate directly with the reduction in its environmental impact, sometimes the opposite, because as a technology becomes more efficient, more people will start using it. And as the usage increases, that will offset the efficiency gains it once made. And we can see this directly with LLMs or AI, because, for example, by December of 2024, OpenAI claimed that they received more than 1 billion queries per day. By June of 2025, they said they received more than 5 billion queries per day. So they need basically to do efficiency improvements almost 5 times in order to scale up to manage the scale up in terms of usage, which is of course not happening. So I don't know, the saying that AI will become more efficient needs to be taken with a grain of salt. And then we need to talk about the importance of batch size, which is something I think can be promising, which is basically that if we increase the batch size from 8 to 16 or from 4 to 8, that can reduce the environmental impact significantly. And I think we're all willing to sacrifice a few seconds, extra few seconds every time we're talking with ChatGPT or something for the betterment of our environment or to protect our environment. And we do think that with the new GPUs that will be released, their VRAM will increase, making it possible to have a bigger batch size. And that will help us mitigate these dangers on our environment. And then we need to talk about the electric liquid cooling and renewable energy. We believe that regulations and policies surrounding these concepts can be very helpful. For example, making big data centers rely even partially on the electric liquid cooling instead of water can actually preserve our water resources significantly. And of course, making them use renewable energy instead of relying on the national grid that can be coal powered can help us mitigate a lot of issues. And now we need to talk about the limitations or shortcomings of the paper that needs to be taken into account in future work. Firstly, energy consumption of inactive GPUs. As I told you, some models only need like 1 or 2 or 4 GPUs. And as you know, the server of DGX has 8. So the remaining 6 or 4 GPUs, what are we doing with them? They are consuming energy even when they are idle. However, we have no idea if they are being deployed to run other models, they're just staying idle, or they are even using them for other tasks besides machine learning or AI. As long as we do not know that, we do not want to include this part in our paper because it will lead us to make some assumptions that we're not sure of. And now we need to talk about the location-based versus market-based. Although I do believe that the location-based is more accurate and more sound, I think putting them side by side can actually give us the full picture surrounding the environmental impact of AI. Therefore, I believe doing this kind of initiative can actually be helpful. And of course, company-based versus region-based. For now, we relied on company-based most of the time, and in case we didn't have data, we relied on the most energy efficient data centers out there. However, I still do not believe that that paints the full picture because, as you may have seen in Professor Wren's paper, even in the same company, choosing different data centers can have a significant impact. Therefore, I do believe that using specifically each data center environmental multipliers for each model can help us paint the full picture or get close to assessing and estimating the total environmental impact of AI. However, as long as we don't have much data about the subject, that makes it pretty hard to measure. And of course, scope 3. I do think that scope 3 is one of the most challenging things, especially regarding this technology, due to the lack of transparency surrounding the technology in itself, and specifically this scope. I hope future research can include this thing, and I hope AI companies will become more transparent regarding this aspect. And finally, I don't know if you guys are on the same social media side as I am, but I've been seeing all the time AI generated videos, like someone cutting a planet or someone, I don't know, doing every kind of thing. It is kind of funny, but I do not think it's very good for the environment as a whole. We're wasting our environmental resources and our energy resources on this kind of stuff. Therefore, I do think developing a benchmark or a methodology to estimate the impact of image, video, audio generation can actually raise awareness surrounding this issue and can actually reduce its uses worldwide. So thank you so much for your attention. And please, if you have any questions, do not hesitate.
Awesome. Thank you, Nidhal. Let's give a round of Zoom applause. No, it's not as satisfying as in person. And we'll open the floor to any questions. Feel free to use the hand raising feature or post in chat. And maybe while folks are thinking, I have one to start us off. I'm curious, could your work here be easily adapted to look at the training cost as well? Or would that be a whole nother 3-year project?
It can actually be used for that. However, the problem with training is that we have no idea about how many GPU hours the models were trained on, or how many GPUs in the first place they used, making it very hard to compute that. But if we have the data, we can just apply the methodology right away.
Mm-hmm. Makes sense. Thank you. And Bryce, looks like you have a hand up.
Yeah, so my question is I'm thinking about like, well, training these models for our like smaller models for our work on biology. The amount of emissions we create is like so minimal and so small. You're working at like such a large scale, like where would you recommend someone starting if they just want to just report like, hey, here's how much carbon emissions, or here's how much, I guess, energy seems to be like the method you're using the most,
Yeah, we
that
rely
is
on
used that I'm using for my probably much smaller model than like some of this crazy like 100 billion request or whatever it was for GPT, but like uh, it seems yeah. But my question is just where to start. If you just want to estimate just like a back loosely how many emissions you're producing for your own paper.
Uh, so I do think that honestly, compared to AI providers, even if we train models locally, it won't be that significant, honestly. However, if you're interested in measuring that, there are actually a lot of tools that you can install on your local computer or local server, like called Carbon or by joules, that basically tries to measure how much energy you're drawing from the CPU and GPU and so on. And of course, you can convert that to carbon emissions or to water consumption. But as I said, I do think compared to AI providers, it is insignificant, but I do think implementing the stuff in your work can actually raise awareness about the subject as a whole.
Yeah, I don't think I meant, yeah, I don't think my goal is like to, it's more just like, hey, here's a useful exercise I could do that potentially could become something as part of our industry that everyone starts to do. I don't know if I would be the one who started, but I'm sure people are thinking about it. But like that could be an interesting thing that if it was required, like at NeurIPS, that you had to do that, or ICML or anything like that, that could be interesting policy that they'd have to implement. Yeah, thank you for
Of
the
course,
talk.
and I totally agree with that.
Yeah, if I can just chime in quick. I know some people are starting to add to their model cards some of this information, like how much their model's expected to burn energy-wise, which might be a good starting point. I have another question about the DEA metric that you're using. Uh,
Yeah,
so, so yeah, you're using that to sort of balance how smart the model is with how much energy it's burning. And I'm wondering, could you just say a little bit about how you're evaluating the intelligence of the model? What sort of measures are going into that?
yeah, for sure. So 1 second. Okay, so for the accuracy of the model or how smart it actually is, we basically rely on a weighted average of the different benchmarks out there. So, and we actually developed it even further, the dashboard. So basically use MMLU Pro, for example, we categorize it as reasoning and knowledge, math proficiency, and coding ability, making it like give us an overview on how good the model is. And after the paper we just talked about before the session, I do think including social awareness or social intelligence can be very important in this model as a whole.
Oh, interesting. Yeah. And for the input on the left there, is that just like a weighted average of all those things?
We so how do I say this? This is like, for example, a linear regression model where you can have
Oh,
multiple
I see.
variables, and for the one you're looking to get, you only have one variable. So for the input, we basically use how much energy consumption, and by using the multipliers, we try to use the multipliers instead of using like the water consumption or carbon emissions because they are very correlated. So by taking the energy consumption, only using the environmental multipliers, you mitigate that.
I see. Makes sense. It looks like we have a question in the chat from Kine. Could you explain more how increasing batch size can reduce environmental impacts? What choices can an individual user of ChatGPT make, for example, to increase batch size? Or is that something that should happen in the back end of most models?
Okay, so I think Chen will answer this one.
Yeah, sure. So this is a very common issue when you're running on inference or training with any AI models in general. You do have to consider about the batch size. So here we're talking about the server side of the batch size, how they're servicing their models at the server side. And for users, we're only really seeing the service layer, which is the front end layer. And it's going to be difficult for us to really fix the batch size because that's already a fixed number that the servers set up to distribute the usage of their models throughout the GPUs that are available in their data center. So for us, I would say that the batch size is also, I would say they're competing against the time to solve a question during inference. So it is a complex relationship between the batch size and the time to do the inference. So it's like, should we increase the batch size so that we're using maximum whatever we can use in the server so that we can solve this question? Or is this question really worth it to use all that batch size? You see that metric itself can be very subjective. So that is a big question in terms of optimization that the data center definitely has to solve. Because let's say that if you're using the smallest model and you're servicing that to users, but we're only trying to use, let's say, that small model that only takes some tiny batch size, that only requires tiny batch size to fully serve users, then what are we going to do with the rest of the resource that's remaining on the GPU? Can we really solve it so that we can maybe service two models at the same time in a GPU? That's another issue, I'd say, in terms of optimization problem that we definitely need to solve.
I just want to add a point that most of these companies actually rely on dynamic batching. So it changes, like sometimes maybe if the number of users is very low, they can just use a batch size of 4. And if the number of users is very huge, where sometimes you notice when using ChatGPT, for example, that it becomes slow out of a sudden. That's because the number of users is huge and they had to increase the batch size to maybe like 16 or in extreme cases 32. But in order, what can we do from our part? I do think that most of the responsibility should go back to the AI companies, of course. But what we can do is use AI for only specific tasks. For example, not, I don't know, some people use it to ask about the weather or like to ask them, what should I eat today? I do think using it more responsibly is actually good for you and good for the environment as a whole.
And also like that's the biggest issue is that we don't really know what the users are going to use the AI for. Because before it was just, a subsection of a language model that will do NLP task, but now we're doing videos, we're doing all sorts of other things that you can't really just imagine. And you would see that, like, for instance, if people are using a bunch of AIs from Anthropic, so let's say Claude, you will see that sometimes the Claude servers will just blow up. And the reason is because even though they implement dynamic batching, it doesn't always work. That's the issue. When there's a bunch of load at the time of usage, you don't really know that we can't really expect what the users are going to ask all the time. So that's another big issue.
I think
like,
Dan has a question.
Yep.
Yeah, less as a programmer or user and more as a citizen of Earth, what do you think is the path to getting these negative externalities like the carbon and water usage actually regulated so that people who do these massive training and use energy hungry models end up paying an appropriate penalty to provide for actual mitigation? Like what is there a way through legislation? How can we advocate for that?
Okay, so from our standpoint as citizens of the world, I don't think we have much say in this because it's usually controlled by the governments. But what we can do, I do think the least we can do is just raise awareness about this technology and its side effects, like the environmental impact and the dangers it poses on our environment. But I do think raising awareness to the next generation that like they grow up with using AI and how they can use it more responsibly is actually the best thing we can do. And maybe like asking the government to do more regulations surrounding how they develop and how they deploy these AI companies. For example, if we look at the EU AI Act, it imposes a lot of restrictions, regulations on AI companies, making them develop with sustainability back in mind whenever they do anything, which is, I think, the right way to go because we're going with maximal speed right now with AI development. So we're discarding or ignoring all sustainability aspects of this technology. Not even sustainability, even security aspects. We did not talk about this, but the security aspects of AI are also very significant. So yeah.
Thanks so much, Nidhal. Do you have time for just one more question, or do you have to run right away?
No, for sure. I still
Okay.
have.
Well, I just want to play devil's advocate for a second here. What do you say to the person that says, "Oh, a single AI query is like the same as watching a minute of YouTube or Netflix, so why should we care?"
I think I need to open the dashboard for this. Okay, so I don't know, maybe we can go to like, I don't know, like Jegham, where's GPT-4? 1 second. Yeah, so this is only 4 watts, which is actually like, I don't know, you can use it in a microwave when making dinner or something. However, when you scale it up to only 100 billion, which is basically it's basically a month of AI energy consumption, it's basically equivalent to almost 400,000 people annual drinking needs. So even a very small query, and we start talking about medium-sized queries. If we go to the long one, it becomes even bigger and bigger. Yeah, 1 million. So even small ones, it is very insignificant in like per query size and everything. But the number of users using AI is actually, we cannot grasp how many people are using it. This is not only for people using the website. We need to take into account the API and how much people are calling it from the API. And now they're embedding it into their systems, they're embedding it into the computer or your phone, or even like your Photos app where you can just tweak and change some stuff on the pictures. So it's starting to become embedded everywhere. So even if you're not actively using AI, you're still using it. Even when you search something on Google, you have AI overview now, which consumes energy every time you do a Google search. So yeah, it is insignificant per query, but scaling it up can pose a great danger.
Yeah, absolutely. Thank you for that. And I guess I would add to that too. It's not just the scale, but also the regulation factor, because industries like, TV or more well-established industries, they have reporting on these things, and they have ESG reports that will report the energy use of their tools. Whereas AI is moving so fast that we just forgot to do that. So yeah.
One last thing I want to mention, Chris, sorry.
Mhm.
I just want to say that you can download the data of the dashboard from here if you guys ever need it. And you can access the repository on GitHub. I think you can just search for it. And if you didn't find it, I'll send it to Chris so he shares it with you.
Perfect.
Of course.
All right. Well, let's give one last round of applause for Nidhal and Chan here today. And thank you so much again, Nidhal. This is really impressive work and very important. So thank you for joining us.
Of course, and thank you very much for inviting me. And I hope you will do an amazing project and keep me updated about it.
All right. Well, take
Of
care,
course.
everyone. Hope you have a good day.
Have a good day.
Thank you. Have a good day, guys.